anywhere? Good.
Sorry. Yeah. I will absolutely not put it up anywhere but for the students.
Okay. Well, as everybody is typing their names into the chat, should I just introduce myself?
Yeah, maybe now's a good time to start. Why don't you lead off? And Annie, you should introduce yourself too, because they're going to see you probably a couple times more. But
yeah, definitely in March for oboe. Good luck.
Annie, does everybody know who you are and what you do?
Have I talked to this class yet? I don't remember.
I don't think you've talked to this class yet.
Okay.
Oh,
hi.
And let me say one more thing. Everybody in the class, I realize that some of you might be in like really not great internet places, but it wouldn't be a bad idea if you could at least like turn on your video. Maybe we'll just go around and have you guys introduce yourselves real quick, where you're from, what instrument you play, and that way they can at least see a face with a name. So if you wouldn't mind turning on your video, we'll do that with all the introductions. So if Annie, if you want to go first, and then Wayne, you go second, and then I'll start just calling off the students' names so you can see them and they can just give you an idea.
Okay.
That sound okay?
Yeah.
Okay.
I'm Annie Roberts. I'm the warranty service coordinator. No, I'm not. The warranty service manager for Yamaha Wind, Strings, and Educational Percussion. That's a really big title for I deal with a lot of warranty stuff and I answer technical questions for repair technicians, including but not limited to obsolete parts, to methods for repair. My second function is to bother Wayne just as much as possible. So if you ever need anything Yamaha related or even not Yamaha related, you can contact me anytime. I play the oboe.
We won't hold that against you. Okay. My name is Wayne Tanabe. I am the senior technical manager of Yamaha Artist Services. And what Yamaha Artist Services is, it's a brass and woodwind custom shop in New York City. I have been working for Yamaha for 16 years. I am the brass specialist. Part of the jobs that I do is I still do standard repairs. So I am cleaning instruments, taking dents out, just like all of you are going to be doing. I'm also involved with a lot of research and development. And in that, what's part of that is designing trumpets, trombones, French horns. I've just finished with a French horn design project that I've been working on for the last 2 years. We are constantly developing new designs and new models for trumpets, and I'm heavily involved with a lot of those things. Prior to joining Yamaha, I ran my own repair shop for 24 years just outside of Chicago called the Brass Bow. And I've been heavily involved in the repair field. I'm one of these technicians that I'm always interested to see what technology and what other companies, other businesses, manufacturing type businesses are doing. This will sound like I'm bragging, which probably, if you guys are familiar with magnetic dent removal, my good friend Eric Satterley and I are the guys who created that. We hold 2 US patents on the design of the tool. So let's say we're partially responsible for heavy magnets being used in the removal of dents in large instruments. I'm also probably one of the pioneers. I'm not the first guy to ever use ultrasonic cleaning, but I'm the first one crazy enough to order a 100-gallon ultrasonic unit that filtered and heated the solution. For the longest time, all of us have always used chemicals for cleaning. And there was a point where I was trying to figure out how to do cleaning better. So that always involved using some type of acid. So the acids I were using got stronger and stronger until I got to the point thinking, what am I doing to the metal? So that's where ultrasonics came in. So this is probably in the mid 90s that I actually had an ultrasonic company design an ultrasonic for band instruments for my old shop. And, you know, one of the things that always bothered me using the old chemicals was all the stuff that you cleaned out of instrument ended up in this 55-gallon drum. And most shops, we kept these drums for decades. And there was one time when everybody was first being introduced to ultrasonics, I just asked this question: how many of you guys still use chemical cleaning? And, you know, everybody raises their hand. I said, okay, here's the next question. When was the last time you actually cleaned that tank out and changed it? In the last 20 years. One hand went up. Last 10 years, no hands. Last 5 years, no hands. We all did the same thing. We kept on adding water to it and more acid, and we kept on using the same bath. So to me, that was like washing your dishes with the same water for 2 years. You know, it just gets funkier and funkier. And that never made sense to me, that we were cleaning instruments and we kept this same old solution. So that's how I got into that. So I've involved myself with a lot of different kind of technologies, including a computer analysis system for musical instruments, for brass instruments specifically, help pioneer precision valve alignment. So there's a lot of things that I've been involved with, including working for a lot of different manufacturers too along the way. Today, we're going to cover, start with brass instruments with pistons and rotors. I understand you guys have covered some piston repair, and I'm going to touch on rotors, and then we'll get into some dent work. And the dent work that I'd like to show you is what I call unconventional dent work. So let's get started. Okay.
Oh, Wayne, would you mind if I just have them go around and introduce themselves real quick so you can get an idea? Yeah, let me just do that real quick. Natalie, go first. You gotta unmute yourself though, honey.
There we go. Hi, I'm Natalie. I am from Austin, Texas, and I play the clarinet.
Thanks. Alicia, sorry.
Alicia, it's okay. Alicia, I moved here from Queens, actually, in September, and I play clarinet. And Shelly used to work on my clarinets. So, yeah.
Hey, Taylor.
Hi, I'm Taylor. I'm from Sacramento, California. Play saxophone and clarinet.
Great. Brendan.
Hello, my name is Brendan. I'm from Syracuse, New York, and I'm a vocalist.
Jackson.
Hi, I'm Jackson. I play saxophone and clarinet and this wonderful Yamaha recorder. It's on my desk.
Davis. Davis, I'm going to come back to you. Ian. Ian, you're muted too. Well, while Ian's figuring that out, Davis, Ian's mic isn't working. Davis is from Central Arkansas. Davis waves. He plays French horn and tuba. Ian's mic isn't working. He's from the Sacramento area. He plays trombone, hence his picture. Where did I leave off? Aster, go ahead.
Hi, I'm Aster. I'm from Northern Washington, where I actually currently am, and I play trombone and some other weird stuff.
All right.
And you
Marlene.
can probably see my cat up there.
Sorry. Oh yeah, cat. Okay.
Hi,
Marlene,
my
sorry.
name's Marlene. I am from South Texas, and I play the flute.
Awesome. Sophia.
Hi, I'm Sophia. I'm originally from Sacramento, California, most recently from Nevada. I play bassoon and oboe.
Dylan. You got to unmute.
There we go. I'm Dylan Seaman. I play guitar, trumpet, drums, and I'm from Renton, Washington. And sorry I was late. My computer is really slow.
All right. Nate.
I'm Nate. I'm from Portland, Oregon, and I play Barry sax.
Awesome. Frank.
I am Frank. I'm from Seattle, and I play double bass.
Nice. Derek. Derek.
Hi, can you hear me?
Yep.
Yeah.
Hi, my name is Derek. I'm from Seattle, and I play oboe.
Great. Jaewon.
Hi, my name is Jaewon. I'm from South Korea, and I play trumpet.
Okay. And Jolene.
Hi, I'm Jolene. I'm from Philadelphia, and I play saxophone.
Okay. I think that is everybody.
Excellent.
Okay. All right, Wayne, take it away.
Let's see. Let me see if I can advance. There we go. Now I got to just figure out how to get rid of all this other stuff here. All right. Piston and rotors. One common repair when all of you get out there and start working the field, there are going to be two things that you're going to be dealing mostly with brass instruments. Dents is going to be the number one thing. Piston problems and cleaning. Those are the probably the big three. One important lesson that I've learned in all the years is to pay attention to what's going on when a customer comes in and tells you, hey, my valve is not working. You ask which valve, my first valve's not working. So your initial reaction is just to look at that first valve. But my advice to you is look at everything attached to that casing, because a lot of times the problems are not just the valve itself, it's somewhere else. It's very similar if you have worked on woodwinds and somebody tells you, hey, my middle G on my sax doesn't work. Do you look at the middle G or you look at everything above it? There's so many factors here. And a lot of times the customers draw your attention to one thing, but you need to always kind of take a step back and look at the entire picture. So that's why I kind of say, look beyond the stated problem. This is the one thing that I've learned, a customer brings in and points to one thing and that's where I'm looking, but I don't notice all the other things that are going on. So it's important to pay attention to everything. So, okay, let's start with valves and rotors, specifically valves. If a valve is not working, what are some of the reasons a valve will stop working? You can put that in the chat, or if you just want to shout it out. Any answers? No? Okay.
In the chat.
Sorry.
We got casing dent and dents have been mentioned.
I'm sorry?
Casing dents, not clean.
Yep. Those are
Something
good.
got stuck, foreign object.
Those are all correct answers. One thing that I know when you're dealing with valve problems, it's one thing to fix the problem, but it's also you need to diagnose this where everything is clean, because a lot of times dirt and everything else kind of hinders your observation about what exactly is going on. So when somebody brings me an instrument and a valve is not functioning, one of the first things I do is actually clean that instrument so I can test the piston itself dry with no oil or anything. Oil sometimes will hide a problem or make something that hangs up a tiny bit, it seems to work flawless. But if it were dry, you'll find the piston, you'll feel the drag in the piston. So that's why I think it's important to clean the instrument and then check everything out while it's dry. Now, one of the things is, how do we determine if a valve is not working? Is it the piston or is it the casing? What kind of ideas do you guys have about like figuring out, is it piston or casing? Is there a way to figure that out?
Yeah.
Swap the piston into other casings, try different valves and different casings.
Ding, 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 gold star. Yeah, if a valve is not working, just pop it into another casing and see if it works. You know, if it's working over here, then you know it's the casing. Or if it hangs up in the different casing that you know is good, then, you know, it gives you an idea which is the problem. So it's very important to figure out which part of these two components is the problem. So great answer. All right. I'm pretty sure you guys, Jessica told me you guys have been working with the piston sleeves and the ground mandrel. And these are very good tools. Now, every manufacturer will make a piston at a certain diameter. And luckily, the Freeze company makes a ground casing sleeve that fits this exactly. Now, you need to have the correct sleeve with each piston because the fit of the valve is important. If the sleeve is too loose, this tool does nothing for you. And obviously if it's too tight, it's not going to work. Now, most of you know how to use this. You take your damaged piston and say you put it in, it doesn't go in from the bottom. Typically what I have seen probably half the times a player is actually cleaning their instrument at home and they drop the piston on the floor. So the bottom of the piston gets dented. So if you get your sleeve out and you take your piston, the bottom's dented, it doesn't go in. So if that happens to you, go in backwards until the valve hangs up. And that you can basically press that in there, then start tapping away and get, and start doing your dent work. So depending on how the piston was damaged. Now, let's see. Do you guys know how much difference there is between the outside diameter of a piston and the inside diameter of the casing that it fits into? Anybody want to take a guess?
About 1,000.
Perfect. That's exactly right. So what does that mean? 1/1000th of an inch difference. So if this piston is 664 thousandths diameter, the casing is 665. So basically what that's telling you, the space on either side or around the piston is 1/2,000th of an inch. It's not a lot. So it doesn't take a lot to get a small ding or dent in the casing, or they drop their trumpet and they crush in the bottom of the threads for the piston to hang up. So that's very little space. Why that is important is the way the instrument works. You would think if you overlapped or you made the casing really big, that the piston should work even better because there's so much space. But the exact opposite actually happens. If there's too much space, the piston going down is fine, but then on its way, it can tilt this tiny bit and then it stutters on the way back. So overlapping is not a benefit to you. So using the right lapping compound, and we will get into that in a little bit, is essential. And what I mean by that is lapping compounds come in different grits or different abrasive sizes. And the size that's correct for let's say a professional trumpet is about 1100 grit. Anything coarser is only very slightly too large for that space. I want to use a compound that fits in that 1/2,000th that's space around the piston. I hope that makes sense to you. But looking at this chart here, manufacturers state anywhere from 1/1000th to 1.5 thousandths, which I'm a little puzzled by the 1.5 thousandths, and I will explain why in a little bit. Our instruments were just subtly tighter by a 10,000th of an inch. We are just a little bit tighter. In all the years when I had my own business, one of the things that I used to do was rebuild pistons. So a customer would come in, trumpet that they've been playing for 30 years. Now the valves are all worn out. Over time, that piston will wear the casing, and the casing gets too large, and all of a sudden the pistons are not reliable. They stutter on the way back, they stick, they do all kinds of things. And what I found that if that clearance goes from 1/1000th total clearance to 1/1000th and a half, it's right here is the threshold where pistons start to become unreliable. So it is a good idea to know what you're dealing with. There are too many times where you'll get a customer come in and they're saying they have a valve problem. And what you want to make sure is this piston is not too loose to begin with. This is what I call the pothole or landmine. The second you as a technician start working on it, now you own that instrument. If there's still problems, now they're your problems. So it's best to avoid problems. And why I'm telling you this, if the piston is really loose to begin with, make sure you don't guarantee you're going to fix this. You're going to do the best you can. You have to leave the expectation that this may not get fixed because of the condition of the piston. The correct way to figure this out is measuring, but in all the shops you'll go with, I don't know how many shops that will have the measuring equipment, meaning a digital, not digital calipers, a micrometer and telescopic gauges. Now, here's a unofficial way to kind of determine, is the piston too loose, or could this be a problem for you before you start actually working on it? If you take a piston that they say there's a problem, take the piston, push it all the way down and grab the finger button. What you want to do with the button all the way down, see if you can move it from left, right, forward, or back. If you can actually physically feel movement. On a tight valve, you cannot feel the piston move at all. But if you can actually feel it shift from side to side, this could be a problem where you won't be able to solve it. And it's important to know this so it doesn't blow up on you, where you return to the customer and they're going, you didn't fix it right. They should know ahead of time, this is probably something that you can help, but maybe not fix. If there's too much clearance, this is kind of a warning that this might not be fixable. So I just want you guys to know that, to save yourself personally some grief from a customer, because nothing worse, because like I said, after you touch it, you inherit everything about that instrument. So it becomes your problem or your boss's problem. So know this. Okay. This is where in rebuilding valves over the years, and I sat down one time, most of the valves I rebuilt, and this is not to throw the Bach company under the bus, I probably have rebuilt over 650 sets of Bach trumpet valves in the 24 years that I had my shop. And what that involved was either plating the old pistons up and getting them honed, or you can buy oversized pistons from Bach and then fit those in, but you need to have the honing equipment and you need to be able to measure everything. So that's where I've come up with this number of 1/1000 and a half. In doing all this work, the guys that work for me and myself, when we would measure everything, and if we found things over this 1.5 thousandths, it was time for a valve rebuild, because most times the valve was not reliable for the customer. So I hope that makes sense. It's not that much of a difference. You know, we've gone from 1/1000ths to 1/1000th and a half of clearance. So it's just a tiny bit of wear. And what kind of happens as the player plays, they tend to pull the piston to the one side. So the piston gets tilted and the casing kind of gets worn in an oval. If you think of the cylinder, it gets tipped and then it gets this oval pattern kind of inside the casing. So that condition contributes to the stuttering or the valves going down. They hang up for a half a second, then they pop up, you know, and for a playing musician, this is a problem. So are there any questions about that? Okay.
Quick question.
Yeah.
Is the material that lines the inside of the casings, is that a harder material than the material used to line the valves? Like, for example, steel is a much harder material than brass. Are they made of the same kind of material that have the same level of hardness, like a Rockwell scale, or?
That's a good question, because things like brass on slide tubes is actually a slightly different brass than what's used in the casing. What's used in the casing is slightly harder. If we're used, a scale, these are slightly harder in its strength. Tubings and crooks, it depends on annealing or heating process and things like that. But in general, casings, that material is pretty hard. But then you have the Monel piston. This is actually slightly harder than the casing itself. But here's the crazy thing. Pistons will wear because if you build up debris and things, all the grit that builds up inside of a casing, they get embedded into the softer material, get held into the softer material, and then start grinding on the harder material. So the pistons sometimes wear more than the casing. Does that make sense to you? That all that abrasive or all the grit gets stuck in the soft brass, so it acts like a file or a rasp as this valve is going up and down. All those hard particles are being held in the casing, just grinding the harder material on the piston. So, most of the time you get more of the wear on the casing, but pistons definitely wear down too. And you're usually, if somebody brings you an instrument that's in that area about 25 to 30 years old, that's where you start to seeing a lot of these problems. Not to kind of brag about Yamaha, in all those years that I was rebuilding pistons, I think I rebuilt 3 sets of Yamaha pistons in that same time. And these instruments were just as old. It's only because the Yamaha piston starts out tighter to begin with. So there's a much longer lifespan. So it's not like we're doing something superior. We're just starting out tighter. So you're going to gain a lot more years out of the same age of a piston compared to our good manufacturer competition, Bach. Bach makes good instruments. I'm not trying to say we're doing something better. It's just where you start makes a big difference. So thank you for that question. Now, determining that 1.5 thousandths, how do we do this? We're measuring. And if I'm rebuilding a set of pistons, and it's someday in some of the shops that you go into, some of the shops will do this. So I'm sorry. But first, we're measuring the pistons. I usually make 2 measurements at the top of the piston and 2 at the bottom, 90 degrees to each other. Then we measure the casing. That is done with a telescopic gauge. And what a telescopic gauge is, it's an adjustable, it's a gauge that has 2 pistons, and you put it into a cylinder, and there's a knob on the end that you can lock, and it'll lock those 2 movable cylinders in one position. Then you can measure that. So by measuring twice at the bottom and twice at the top in 2 different directions, I can get a pretty good idea what is the size of the casing and what is the size of the piston. And what I do is average all this stuff out. So if I take all my measurements, and we're measuring down to the 10 thousandths. Now, you may or may never come across this in your repair life, but if you're working with somebody that's very important and it's critical you get this right, you really need to have the tools. In this particular example, the difference between the casing and the piston, I'm almost at 2 thousandths of an inch clearance. This is a problematic piston that will hang up. It also when a piston becomes loose, yes, the instrument will still play pretty well, but it doesn't respond as fast. It doesn't have as much color. It's, some guys get used to their instrument being so loose, and changing it to something where it's tight again, their response is better. It throws their timing off. So sometimes it takes a player that really knows their instrument a little bit of time to get used to a rebuilt piston. So, unfortunately, it used to be easy to get a set of pistons rebuilt. If you guys are familiar with Anderson platers, we used to be able to send pistons there and ask them, I would like these pistons to be at 665, and they would plate and hone it right to that size. Anderson stopped doing that about 2.5 years ago. So I don't know where anybody goes now. There's very few shops that actually can rebuild a set of pistons. Osmond Brass out in Boston is one of the only shops I know of where it's reliable. And Steve Winans, Dr. Valve in Chicagoland area. Those are about the only two places I know where they're bulletproof. You can send them there, they're going to be done right. So I just want to show you, how this measurement thing is done, and it does take a little bit of equipment. Does anybody have any questions regarding this? Okay, let's move on. And
Hey, Wayne.
yes.
Jessica did mention that Dan Oberlo, or I'm sorry, I might have said his name wrong, in North Seattle does do all that.
Valve building?
Yeah.
Yeah. I've actually spent some time with him at his platers, and I've watched him hone valves, and he's got all of these kinds of tools to measure, and it's quite an impressive setup.
To be honest, he's the only one I know of too.
Okay.
Yeah.
I just don't know of hardly anybody that has invested in the equipment to even do any of this stuff. I mean,
And even when you get that equipment, the learning curve on it is monstrous.
Yes, and I know John Huth has dabbled in that from Red Wing, but I'm not sure if he ever really did anything with that. But I think Red Wing has a honing machine, or at least they did when I was in school.
Okay, it does take quite a bit of equipment, honing equipment, to hone these plated pistons back to being a cylinder, especially if a piston is really worn. How they're built up in size is they're actually copper plated first and built up with a few thousandths, and then hard nickel over that, and then you hone that and keep on honing that until it's a cylinder again. Okay, let's see. Let's keep on going. Jessica, you guys have not really covered lapping, have you?
We just talked about it this morning.
Ah, perfect. Okay, so what is the purpose of lapping? Anybody?
To make the piston go up and down, clearly.
It's kind of like sanding. I mean, it's liquid sandpaper that you brush on something and will hopefully remove burrs, defects, and whatnot, but it removes material as well. So
that's why my first point about making sure you use the right lapping compound, because we have so much space that exists normally between a piston and a casing, and using that 1100 on a piston. When you get into the larger instruments, your baritones, marching horns, tubas, the space is more like 1/1000 of a half, and you can get away with using 900 or 1000 grit. And one thing to kind of point out, most shops still have the old style lapping compound. Now, what I mean by that, lapping compound has a certain kind of abrasive in it. Most shops, most good shops, used an abrasive or lapping compound that had this abrasive called garnet. And what garnet is, it's described as a fracturable material, meaning it starts out at a certain size, and as you use it, it begins to break down finer and finer and finer. It doesn't stay at the same size. And the beauty of garnet is with soft brass, if the abrasive is too hard, it will embed itself into the softer material and get trapped in the soft brass. Garnet will not do that. I think a lot of the suppliers, our suppliers, have run out of the garnet lapping compound. So what they've replaced that with, I am not sure. I think it's silicon carbide. The nice thing about garnet is when you first put lapping compound in and you put that piston in, you can kind of feel that grab, that initial grab, and you can feel it doing something. But as I was saying, garnet breaks down to be finer and finer. And the more you do it, everything gets smoother and smoother. So you have a feel about what's going on the entire time. The new stuff they replaced it with, you really don't have that feel. You could sit there and do it and you have no sense if, is this getting smoother? You just know you're doing something. And that's really about it. So it's harder to tell if it's getting better. So just kind of be warned, but enough shops, most shops do not just go through lapping compound very quickly. So most shops will probably be good for the next 10, 15 years. But at some point, they're going to run out and they'll be switching. And it will be a different game, believe me. I've lapped enough pistons in my life and I still have a lot of garnet lapping compound, so I feel lucky. But I have tried the new stuff and you have less feel about what's going on. And that's the thing, is knowing that feel as you're lapping, you kind of, with garnet, you knew when you were finished. With the new stuff, you just had to clean it, put it all together and see if it worked or not. So hope that makes sense. Okay, purpose of lapping, there were a few things already mentioned, but lapping is a precision tool used to perfect the fitting.
Hey, Wayne, I'm sorry. We had a question about silicon carbide, asking if that's glass, if it's like glass.
That I actually do not know the answer to. Silicon carbide is, I can tell you this, silicon carbide is used mostly for ferrous metals, steels and things like that. That's where it's used most.
Yeah, that's where I was familiar with it from. I was the one that asked that question. So I was like, isn't that glass type? It's almost like a type of glass. It's very hard and can really eat into things.
Yeah, it is very hard. It doesn't fracture or break down like garnet does. So it stays the same size. So with silicon carbide, I think it's to your advantage to use something finer grit than you would normally think to use, because it continues to cut at the same rate no matter how long you're using it, where garnet just kept breaking down into a fine polish. Silicon carbide, there was one company offering diamond compound, which I just thought was a giant mistake for music. Diamond is unforgiving. It will just cut, and it doesn't give you a margin of safety for you yourself in doing valve repair. If you're going to do valve repair, you want to make sure you do a good job and be able to hand back to your customer something that works. And now, you don't want to hand back something where the piston is too loose and it starts to hang up.
One more thing, Wayne. It looks like I didn't know this, but it looks like Music Medic has a garnet lapping compound available now, which is, I think, new.
They do have it, and I've tried it. I've been trying to get some information from Kurt, like what's the base, and it's one thing to get lapping compound, but the next important thing, if you use any lapping compound, is to be able to clean it out of the instrument. So, the old garnet and stuff that Hetman products used to sell us, I could clean that stuff out with Dawn dishwashing liquid. So I'm always investigating, like, okay, this works, but how easy is it to clean this now? Because some of the stuff will get embedded into the metal you're trying to hone, and it's difficult. You could clean it, put it all together, put some oil on it, and then you pull the piston out, wipe it with a paper towel, and you see all this gray. You haven't got all that abrasive out of there. So I'm still working on Kurt to get more information from that. So this is, yeah, you're right. This is fairly new with Kurt getting this. And right now I'm investigating another company that used to sell it, but they're, I think, selling it again, garnet lapping compound. So I'm trying to find out what's going on. I've been told that garnet was made for a totally different industry. Now, I'm not even sure what that is, but that industry stopped using it. And that was the main reason garnet was being produced in all these different grades. So once this one industry stopped using it, everybody else was just left saying, well, sorry, you can't get it anymore. So I'm looking at another company right now, actually. So if I find something else out, I will let all you guys know. So, all right. Let's see. We've covered this about the clearance, and especially on pro instruments, it's important to use the right lapping compound. So on your top line, I'll just say Schilke fits valves very tight. We do, Yamaha does. Everybody else is around that 1,000th, which is not saying anything about the quality of the company. It's just how we kind of look at valves and what we consider the finished product. So for the Schilkes and Yamahas, 11 to 1200, I think is the ideal lapping compound. It's the right size for that. For everything else, you can use 1,000 to 1,100. You know, a lot of shops you go into, you just don't know what's going to be there until you get there. And sometimes they just hand you a jar lapping compound and the labels come off. And for all you know, it's 700, 600 grit. Yeah, it's going to lap, but it's going to do some, a lot of material removal at the same time. So just be careful and ask questions about that stuff. Okay. Now, lapping compound. This is from Hetman's products. This is what he suggests for different grits and what their purposes are. The only thing he didn't take in consideration is, like for Yamaha and Schilkes, how tight our valves are. So I would put our valves at that 11-1200 grit. It's for final finishing. So, but you guys will have a copy of this. So there are purposes for all these things. It's no different than sandpaper for wood. You use something coarse to kind of get something close. You get finer and finer to improve the finish or smoothness of the material. So hope that makes sense. All right. And we've talked about this, trying the problem piston in a good valve casing and the good piston in the problem. So, but if we discover the piston is the problem, so our solution is to put lapping compound on the piston and start lapping part. So my question to you is, if this is the problem, why are we lapping this? So, but this is, I look at this more from a professional standpoint. I'm trying to fix a problem. And if I have to wear something down, I'm going to wear this down. And if this is not the problem, why am I taking material away from a valve casing? So this is where that Freeze ground sleeve. If you think about this, these from Freeze are perfect cylinders, honed right at the correct dimensions. There are no portholes. They're perfectly round. I'm using this as a what I'll call a lapping sleeve. I will lap the problem piston in the sleeve. So I know this is perfectly true. So I can lap this, and there are a lot of benefits to doing this instead of doing it in the casing. So if the piston problem, let's fix the piston. So our advantages, I target the problem and I'm only taking material away from this. The other thing is I maintain the valve clearance because I'm not taking material away from two different parts. And the biggest thing is, after I get done with this, I just clean the piston. I don't have to clean this as well. So from a time standpoint, I'm saving a whole lot of time that I'm not cleaning all these materials. So does that make sense? This is something different. Nobody ever taught me this, but in thinking about this going, this is the problem. Why am I trying to fix something or use this that's not broken and not causing the problem? Why am I taking material away from it? So I've come up with this, and it's the same reverse way around. If we discover it's the casing's the problem, why am I using the good piston? I'll use the ground casing sleeve and use this as my lap. Again, a perfect cylinder, it's perfectly straight, and I can sit there, lap this. You could lap this, you could lap 300, 400, 500 sets of valves, and this will still pretty much be at the same size because it's hardness, it's the casing that will take the wear, but I will use this through the casing rather than lapping the piston. I hope that makes sense to all of you.
So Wayne, somebody did ask what you just covered, which is, can the lapping compound damage the sleeve? Is there a point though, at some point, you said maybe 500 casings or pistons, but is there anything that you can do that would damage that just by lapping?
Yeah, I mean, for me, I have two of these, same size. One is strictly for dent work and the other is strictly for lapping. I don't use the same one for both processes. And same with the ground casing sleeve. I have one clean one strictly for lapping, and the other one is for doing dent work. So I have the luxury of having two of everything, or at least for us as a manufacturer, all our pistons are pretty much the same size. So I can use, I can afford to have two different one of these things, but you're right. Eventually, this does wear. So does that answer your question? Yes, no.
They're nodding yes. That answers it.
I'm sorry?
They nodded yes, Wayne. You answered the question. Thank you.
All right, before we move on to rotors, you guys have any questions about pistons or anything? We can take a short break if you want, or just move right on.
Power through.
Power through. Okay. All right. Couple things that I would like to bring up about rotors. Okay, if you're working on a Yamaha product, one of the most difficult things with working with rotors is removing the rotor. And part of that difficulty is just taking the stop arm off. Now, what makes Yamaha actually a little different, we actually fit these rotor arms. Most other companies, it's pretty much a pressure fit. I mean, they hammer those things onto the stem. You will find that whether it's a rotary trumpet or a tuba made by Yamaha, you can sit there and take a screwdriver off the stop plate, just put it underneath the rotor arm and pop it up and take this arm right off. Other companies, you have to basically hammer through this. Now, one thing about this, what most technicians do is usually there's a rotor screw on top, and most techs will loosen that 3 or 4 turns and then take a hammer and tap on the rotor screw, the screw that holds this arm on there. And this will work beautifully until you get that one that snaps the screw. Now, I was taught to loosen that screw and just take my hammer and just beat on top of the screw to get the rotor to drop and get this arm off. But in all the years that I worked for a shop for 5 years, and then in my own shop for first couple years, I've probably broken a half a dozen of those rotor screws. And I'll tell you what, most of the times when they break, they're not easy ones to get back out of the top of the rotor. So in order to avoid that, get yourself a steel punch. This one is 3/32, and I think you can use 1/8 inch, but you take the screw out. And then when the screw is out, you put the steel punch in there and tap on this. You can loosen any rotor arm from anything with the steel punch, and you will not break screws. If you break a screw, you've automatically added a half an hour, 45 minutes, depending on, how badly the screw broken or how far down it broke. And hopefully you have the replacement screw. That's the other thing about this. So if you don't have a steel drive pin, you can go to pretty much any decent hardware store and buy these. Can you guys see this? I'm not actually seeing what I'm showing you. So I don't know if you guys are seeing this.
Yes.
Okay, thank you. But driving this out is the best way, because if you break a screw, you have everybody else looking at you going, what did you do? And it could have been so easy, not to waste time and just get all these apart, because there are some of these arms. I can think of, let's see, Con French horns, Holden French horns, where these things, you're really hammering with all you got just to get these apart. So, to rely on the screw that holds this arm on there, sometimes just not a good idea. Okay. One other bit of advice I have is rotor bumpers. Now, most schools, most places, most shops just buy Buna rubber cord. And then you have to figure a way to get it into this holder. And a lot of times it takes pliers, squeezing, pressing, and some of the Buna rubber is so hard, it's almost impossible to get it in here. So here's my piece of advice. Yamaha sells, I don't know if you can see this. This is in bulk. It's our rotor bumper. It's already pre-cut. One lucky thing in the shop in New York is I do not just work on Yamaha instruments. I work, myself and my colleague Tomoji Hirokata, who is a world-class woodwind technician. We're the only Yamaha custom shop that actually works on anything or everything. So we see everybody's instruments. This is the only bumper material I use on everything except for some large tubas. So if it's a Con French horn, a Holden, a Bach trombone, whatever, this bumper material, the pieces are already pre-cut. They're soft enough. Most of them, I can just about push them in with my fingernail. They're tough. They say soft. I've seen this stuff 20 years old, and they're not hard as a rock like some Buna rubber products get when exposed to certain kind of rotor oils or oils themselves. Sometimes will harden that Buna rubber cord. So I don't know if you can see an order number, but this is what I would tell you to use. It would make your life so much easier on just about any rotary instrument you work with. It's real easy to work with. This stuff lasts forever. And it saved me trying to figure out tricks to get that installed in the plates themselves. Okay. Now, Jessica, can I ask you a question?
Yeah, I'm here.
When you do rotors, I mean, what do you guys cover? I mean, the reason I'm asking you this is what I've got in my PowerPoint is more about like getting real heavy into rotors. When rotors wear, you get this end play and you get side play and tightening. And I don't want to start covering stuff that, a lot of techs won't even be doing this.
Yeah. So we actually make a tool instead of using a steel punch to get the rotors out. Okay. So we make that tool. We made a bearing plate tool. But we go over how to take apart the instrument, how to wash it properly with that special brush to get the rotor casings, how to string rotors. Although I do have mechanical link rotor well, soon to be on order.
Do you ever show how to tighten a bearing or
we
like?
do, yeah, we do get into rotor valve fitting. And actually I have a colleague of mine who worked with Overlow for a while. So he got Overlow's like whole system of how he tightens rotors with the collet wedgers to tighten around the stem and the top, and also, you know, to alter the bearing plate. So the bearing plate sits in there so you don't have any hop. So we do go in, but here's the thing, we don't do that till February, and we might not get into the actual rotor fitting stuff till third quarter, depending on how everything plays out. So we haven't touched a French horn or a rotor yet.
Okay, I'm going to just kind of go through this very lightly. And if somebody wants to ask questions, please do. But what I'm going to be covering is rotors wear over time, just like a piston over time will wear the casing. A rotor wears inside the casing. And I just want to show you what wears and where the problems exist. So I'll keep going on here. Okay. Most of you will get familiar with what's called the rotor bearing swedging tool. And that is a tool, it's a collet tool. Basically, this part of the bearing gets loose and it's to swedge this close. It's much like swedging a woodwind key where you squeeze this and this is reduced center on top of the rotor to get the rotor tight inside there again. But my first step is to remove what I'll call end play. Over time, a rotor starts to be able to move up and down, partly because when a lever or a string linkage is moving the rotor, it tilts the rotor like this. So what happens, the hole gets worn in an oval pattern. So this is the reason we have to tighten. Also, a rotor has a bearing surface on each end. Over time, those wear so the rotor can actually start to move up and down. And I think it's more important that we remove this end play. One thing you might not know is most rotors, or just about all rotors except for Texas Con 8Ds, these are tapered. The outside, this is a taper. It's not a perfect cylinder. So the casing is tapered also. So when this fits, you know, you've got this going on, but if the rotor can move up and down, when two tapers move away from each other, it creates a big gap in a space where now the rotor leaks air to the closed position. So that's why I'm talking in this particular PowerPoint about removing up and down play. So hang on a second. Here's a rotor. And these are two spots where we get quite a bit of wear, because this is where the spindle on each end of the rotor will spin. So naturally, this is where you're going to get the wear. You will also get wear on the inside ends on both sides. That's where you're going to get that up and down play. Now, how I approach this a little bit differently. Let's see. The spindle itself and the bearing, wow, I should do this better. The spindle and what it fits in down here are also tapered. Now, in this picture, you see where I have that black circle. If I can surface that, meaning takes the material away, what it allows is this piston to drop, or this rotor to drop down a little bit more. So this taper fits better into the taper that's in the bearing below. I hope that makes sense. I don't know too many guys who do rotor repairs actually do this, but I am servicing that part of the rotor casing to allow the bearing to drop out, to get this taper to fit better in the taper that's in the bearing below. And I'm talking about maybe a thousandth of an inch, a thousandth and a half. It's enough where it returns the tightness of those two tapers. Now, let's see, right here, moving a thousandth to 2,000. It's not a lot. You need some specialty tools that you can buy. I think JL Smith makes a flute tone hole leveling disc for the Trill Key tone holes. You can use that to basically surface the bottom of that rotor casing bearing top spot. So that'll allow the rotor to drop down and tighten the taper. And for this, what we're going to do is, well, let me just show you kind of this diagram.
Wayne, can I interrupt you real quick?
Yes.
There was a question about general ratio of tapers.
What do you mean?
1 in X ratio of tapers. I'm not sure what it means. Sophia, would you like to?
Well, yeah, a lot of times when I see tapers, they're listed as 1 in X, like a 1 in 14 taper. That's obviously going to be narrower or shallower than a 1 in 14.
You know, all the different manufacturers have their own unique proprietary shape. So there's not a single answer to your question. Does that make sense?
Yep, our standard lack of standardization.
Do not use the same taper. Some are even proprietary, don't really align to anything on anybody's chart. So I know that's not really answering your question, but that's kind of the reality of what every manufacturer does. Some of it's unique to the instrument itself, so they've just come up with their own version of things. So I hope that answers your question.
Pretty much. It's kind of like the only thing that's standard around here is the complete lack of standardization.
Okay. What I'm showing in this diagram, the picture of the rotor and that red outline is showing the bearing surface and how much space there is. And it's representing what's in the bottom of the rotor casing, or what I call this bearing, I call the bottom bearing. This removable one, I call the top bearing. Different manufacturers have different names for either end of this thing, but you know, the fixed bearing I call the bottom. But when the bottom one wears, I'm showing you why I kind of lap this one surface, which I'll come up right here. Where that blue line is, that's what I'm surfacing. So if I remove a thousandths or a thousandth and a half or 2,000ths, what kind of happens here is it allows the rotor to drop in and this taper now to be tighter. So I hope this visualization helps with why I'm doing this. So that takes care of the bottom bearing. The top bearing, to get that closer, is I am going to basically machine or abrade the top of the rotor casing. So you can either put the bearing in a lathe and machine the underside of the top bearing. You have to have a decent lathe that'll spin that rotor bearing concentric. That's the problem. You know, a lot of shops, they have decent lathes, but to get something to spin concentrically that was made on a different machine is not always possible. So I hope that makes sense. So the easier thing to do is I can take a thousandths off the top of the rotor casing. So top of the rotor casing can be serviced to allow the top bearing to drop, and this will help reduce the end plate. So there are plenty of rotary sax tone hole tools that will do this job. You know, Freeze, JL Smith, everybody's selling these discs to surface tone holes. You can use the same type of tool with one of the pilots to take a tiny bit off the casing itself. So in doing that, I can drop down. Now, I don't know if Ed Kraus still sells this tool. Mr. Kraus has gotten out of selling a lot of different things. This tool only existed because I asked him to make this. So if he still sells it, I am unclear.
I don't think he does. He is really trying to pare back on tools, and if he does, he has like one set left, but I really don't think he does. He's really trying to just focus on pads and bumper material and stuff like that.
As a substitute, you know, any of the sax tone hole tools that you find, you can use those. As long as you have some kind of pilot to keep the abrasives kind of centered in the rotor casing.
Wayne, we have a lathe question. Sophia, can you go ahead and unmute and ask your question?
Yeah. So if you got a 4-jaw chuck for your lathe, shouldn't you be able to set it up to turn concentrically if you're using a 4-jaw independent? Because I know 3-jaw automatic self-centering chucks rarely ever center. I got a lot of experience and background using these things, so I was immediately thought 4-jaw chuck, you can.
Yes, you have a 4-jaw chuck and you have a dial indicator, you could dial this in to spin dead center.
Not many shops are going to have a 4-jaw chuck, even if they have a lathe. I will put that out there.
Oh, okay.
Yeah, I mean, it's either that or there are 6-jaw chucks where the entire chuck can be adjusted. It's kind of like that 4-chuck idea, but instead of moving the jaw, you're moving the entire chuck. And I used to have a small 6-jaw on my small Logan lathe that I could dial anything in to be dead center. So yeah.
Hey, I don't mean to cut in here, but I can't have this meeting go till 2 because I have to jump to another meeting at like 1:45. Okay. So I'm not, and we have not gotten any French foreign stuff as far as this goes. And it'd be, you know, I'm not trying, just saying if we could like maybe get out of this and get in, you know, or move this along a lot faster and get into dent land. Sorry, everybody.
Okay, thank you. All right. Before we get into dents, do you guys want to just go on? Do you want to take a short break? I mean, do anything you'd like.
I'm good. Straight on.
Just keep going. All right. I'm going to try to make this quick. Thank you guys for hanging in there. We've been here a while. All right. Okay. I'll try to make this quick. A lot of the things I'm going to talk about with dent work is what I'm calling unconventional dent removal. I'm sure you guys have had your share of putting dent rods, dent balls, all these different tools to remove dents. I'm going to show you a few different things or different ways of thinking about things. Okay. Customer comes in and they have this real minor dent. Say this is a brand new silver plated instrument. As a technician, what your wish is that you would go in with the fewest number of dent balls, just get this dent out and then leave it alone. And sometimes, how do we figure out what dent ball will fit exactly in that one spot? And I would like to just show you a way to kind of figure that out. All right. You know, I'd rather have a dent be really serious and big than these tiny little Dording kind of dents where you barely see it. But you get these customers who kind of freak out about every little thing, and it better come out almost perfect or where they can't even tell that you were there. You know, you will get customers like that. Most days when you're working in the shop, you are the technician. But every now and then, and you'll remember I said this, sometimes your client is the technician. And this won't make sense to you now, but once you get out in the field, you're going to meet those customers who will really kind of push your buttons. So be ready. All right. How do we figure out how to pick the dent ball that's going to go right there without going through 5, 6, 7 different dent balls? Okay. The way I would do this is measuring. Now, there's a way to do this by measuring. In this example, you can see I'm measuring the crook of a trumpet bell. One direction, it's 541 and almost 542. The other direction, it's 510. There's this huge difference here. Like 30 thousandths of an inch. And why is that? Whenever you bend something, this direction gets more narrow than this direction, or the diameter here gets wider in the bend. It's a natural occurrence when, even if you fill it, it's hard to get a perfect cylindrical bend. But this is a normal example of, when a bell is bent, there could be this much difference. It's not a perfect cylinder. And that's why sometimes when you are taking dents out of the crook of the bell, that sometimes it's like you're tapping and you feel like I'm right on the dent ball. You get to the side and you're going, no, I'm not on the dent ball. This is one of the reasons why, because it's wider one way than the other. But the reason we're measuring this is to become clearer in a second here. 541, 510. So we got difference about 30 thousandths of an inch. So if we measure the diameter and we average this out, we come somewhere in the area of about 525. We average that out. Now, what do I do with that number? The thickness of metal used in brass systems is somewhere between 16 to 25 thousandths. So how does that help me? If I know the outside diameter and I minus, two thicknesses, a thickness on either side of that dent ball, then I can actually pretty much guess within one dent ball finding the right one that'll go right under that dent that I was gearing for. So in this, I would tell you if our average is around 525, I'm going to average the average thickness about 20 thousandths. So if there's two sides of that, so I'll minus 40 from that diameter that I measured. So I come up with 485 here. Now, that dent ball should go right under that dent right there without you guessing. You'll either be right underneath that dent or within one dent ball of it. So this is one way to kind of figure out to exactly get the right dent ball under that one pesky little dent. So.
Okay, I'm going to interrupt you, Wayne. To the students, I have been in this industry since 2008. This is the first time I've heard this. You want to write this down and put it in your back pocket, because this would have saved me an incredible amount of time throughout my entire career. This might be my favorite piece of information I have received in a long time.
This is one of those things. I was just sitting there one day and I had this pesky customers and brand new instrument, and you're trying to do as little as possible not to create more work or try to put as few things inside the instrument, because this person was very particular about everything. So I sat down and figured this out, going, wait a minute, I know the average thickness of the metal. Can I use this information? And I sat down and I figured this out. And I was kind of surprised that I actually, first time off, actually picked the dent ball that went right underneath the dent. Now, in saying all that, are you guys familiar with all my dent hammers? I have coated with something. I have this hard red plastic that Ed Krause used to sell. There's a plastic or ultra high molecular weight sheet that's self-adhesive that Voto, I think, still sells. All my hammers, I do not use a plain steel hammer. I do not like Delrin hammers. I never have. I don't think there's enough weight to it to impact a dent. But I've had this same red plastic for the last 5 years on the hammer. Hasn't come off. You can hit as hard as you want and never leave a hammer mark. So on silver, on brass, whatever, I can sit there and do all this work and you don't get any hammer marks. And that's part of the way I avoid leaving marks, because my goal is to make it look like I was never there. And that's hard sometimes depending on the dent. But figuring this out, doing dents here, and the other instrument that really I don't like working on, taking dents out, are flugelhorns. Flugelhorn branches and bells, it's a constant taper. So you get one dent ball that goes right where you want it. The next one goes way past where you need it. So you have to get very creative sometimes to figure out how to get a dent ball exactly where you need it. Okay, moving on. Here, this seems simple enough, but no dent rod reaches this. So what are our choices? Customer wants this dent out. Well, our only choice is to take this apart. Or do we? And to make this worse, if you put a dent ball in the tubes, the crook inside diameter is actually larger than the tubes attached to it. So you can only get so big of a dent ball in there. All right, here's my solution. It's basically, you can put the largest dent ball that you have inside there, and with a magnet, and there's a magnet, rare earth magnet inside this tube. Basically, if the ball is loose enough and you can get underneath the dent and you can tap this, what happens as you tap, even though the ball is loose, that tap, the ball drops away and then pops back to the magnet. So in some sense, every time you tap, the ball is going away, coming back and hammering back up at you. Now, you can take that dent out by doing this with a ball that's actually a dent ball that's too small. So here I am with my tool, I'm tapping on this, and that's the end result. I got the dent out. Now, what I will tell you about this sounds easy. This is painfully slow. You'll be tapping and think I'm doing absolutely nothing or I'm doing more damage. You'll be tapping going, man, nothing's happening. But if you do it long enough, you'll start to see this dent start to come out and get smoother and smoother. And then you start to learn how to, as you're doing this, moving the magnet back and forth so you're covering more of an area and tapping on it. But you can take that dent out. I didn't have to take it apart. I got the dent out. It comes really handy on a lot of the large tubas that have really soft crooks. You can take out a whole lot of stuff that you cannot reach with a dent rod. So this was the customer's French horn, wanted it, they were actually waiting. I said, well, give me a few minutes here. It took me about 15 minutes to take that tiny dent out using a magnet and a dent ball inside that. Let me show you another example. This is a euphonium. There's no way you can get a knuckle tool or a dent rod to this one dent. Same thing, I found the largest dent ball that would fit in there, attracted with my magnet, tapped on it, and got the dent out. One thing I would suggest when you're doing this, wherever the dent is, take a Sharpie and mark a line, the center one direction, center the other direction. That's outside where you're holding the magnet. So you have an idea that your magnet is right over the center. So draw yourself a couple witness lines to kind of make sure your magnet is in the right place. But you can take dents out, but it is really painfully slow in how it reacts and how the dent comes out. It's very slow. So, all right, here's a couple of examples of some really bad dents. So you can insert your joke about the trumpet playing flat here, but this is, I think a guy was zipping up, well, he thought he zipped up his triple trumpet bag and he threw it over his shoulder and launched his trumpet across the room. So what do we do to take this dent out? Most techs will try to find a very skinny dent rod, shove it in there, and try to start pushing this dent up. And what normally happens, wherever the tightest spot is, you get this terrible stretch bulge from the dent rod. Now you got another little ugly thing that you got to try to figure out how to clean up. Is there a better way to do this? Is there a tool that could help us out with opening this up? Okay, that's that same trumpet, and that's from the side. You can see how flat that thing is. And, you know, when you flatten it this way, the other direction, it gets wider. So how do we do this? What tool do we use? Come on. A tapered rod. Now, I've already explained, you push a tapered rod in there, you'll get this terrible bulge where the tip of the rod hits the narrowest point. How about a set of pliers? Believe it or not. So what do I mean by that? Are you guys familiar with these pliers with the nylon jaws?
I have them. I haven't showed the students them yet.
Where do you source those?
If you just
Amazon.
type in Amazon PH165, you'll see them for $14.95. Okay, if you can see these pliers, let me just talk about these first. What these are great for, say you're replacing a lead pipe on a trumpet and the S braces got really bent up. You want to be able to straighten it without ever leaving a plier mark. These are your pliers. Straightening out woodwind keys, the lever got bent. You can grab this thing as hard as you want, straighten things out, and never leave plier marks. They're big enough that if you have a stuck rotor cap, you can grab it, loosen the rotor cap, and not leave a mark. So if you don't have these, I think this is a good investment. So half of you are probably on Amazon right now placing. I've had guys actually on their phone order them during my clinic. So, and if you're smart, you'll also order the replaceable jaws, because these nylon jaws, there's a screw that holds them on and they can be replaced too. So these are great pliers. They'll allow you to do a lot of things and nobody will know that you use, you know, something, you're not leaving marks. That's the important point. In this particular instance, what I am doing is where it's widest point, I'm just taking the pliers, and you have to be very careful. The widest point, I'm just doing light squeezes. And I can take where it widened out and start squeezing that back, and you will see the roundness start to come back. Now, the other thing is Allied Cells. Oh, I think I have this. Hopefully I have this in my presentation. Allied sells these pliers. They look like giant swedging pliers for basically brass tubing. Basically, if you were to expand a trumpet tuning slide or something, and let's say you accidentally went too far, who does that ever happen to? You can actually swedge the tubes back down, but these pliers I have lined with the UHMW or the Teflon sheet. Both sides are lined with that. And if something gets really dented, you know, the sides will go out wide. I can sit there and take the wide side and slightly squeeze them back, and you'll see where it got really crushed. It starts to open up without you even putting a dent ball in there. So I hope that makes sense. Okay. Another example of the pliers is if you look at this trumpet bell crook on the right, there's a dent. And what always happens when you get a dent back here, the sides go out wider. So if you look at that right above the dent, 530, and I think right on the dent, it's 19 thousandths bigger. So if, there it is, T4065. If I take my Teflon line pliers, rather than just start shoving dent balls in there, I'm gonna very lightly squeeze this back down, measure, squeeze, measure. And I went from 549, whatever it was, down to 533. So I almost got it back to round. Now the dent is actually easier to take out. So that's by just using this. And if you ever decide to use this, be careful, do it slow, very light squeezes, because as much as you can do good work, it's very possible to do some very ugly things with these, okay? Just like magnetic dent work, you can do good and you can do evil with the same tool. So it's all in your hands. Does that make sense? Anybody have any questions about that? These are just small things to make the dent work come out better, because otherwise you're relying on a dent ball to actually lift the dent up and bring the sides back in. If I bring the sides back in, it's easier to get the right dent ball size in there, and the dent will come out actually better. Okay. Now this is an actual repair, and remember I said most times you are the technician, but sometimes the customer is. This was one of those cases that I had. What tool and method should we use to start this repair? Oh, okay, I'm sorry.
Cable leg? Sorry.
I forgot, the player does not want me to remove the front brace. He does not want me to unsolder it, believe it or not. And normally I would just unsolder the brace and just go at this thing. But this guy was a big artist, and all right, I like a challenge. So what do we do here? Well, we need a special dent rod. Yeah, okay, from the top. This is how badly bent over it is. So I just want you guys to get a good idea of what I'm dealing with here. This is my solution with this. I took a dent rod and made a spade tip on that. Okay, now, most of you are going to go into shops and say, well, we don't have a dent rod we can sacrifice. Okay, if you have a straight burnisher, you could basically do the same thing. Just put the tang of the burnisher in the vise, and I'll show you in a second how this kind of works. So with the spade tip on the front of that dent rod, I can insert that into the bell. Let's see. Okay, I'm going to just show you just continuous pictures of this rod just going into the bell to straighten this out. Okay, it first enters, is getting a little straighter. Once I got that dent or the tip of it past the dent, now I can just rotate the trumpet around that dent rod and round that out. Instead of pushing the narrowest dent rod I could, making more marks. This is just using that same dent rod. And now I'm just pushing the bell back against the rod. And that's where I ended up, just using that dent rod to open that up. It's a big difference from where I started and didn't do additional damage. You could kind of do this with a straight burnisher to open that up. Once you get this tip of this past the deepest part of the dent, just rotate the bell very slowly on the burnisher. It will sweep open that closed spot a little bit. Does that make sense to you guys? Because you will get ugly stuff like this. All right, this is my finished product without unsoldering the brace. A lot of that was done with, let's see, do I even have it? Here it is. I have a small plate burnisher. It has UHMW on one side. So what I'm doing with this little tool is I'm putting this edge against the side of the brace and tapping around it with a full-size dent rod inside there. And that's how I got the dents out around the brace, by using this. You know, to try to hammer something perfectly next to a brace, you know, without hitting the brace is impossible. But having this little metal plate with UHMW, you can hit as hard as you want and not leave a mark. So that's the finished product. Yeah, there's some stretch marks and stuff, but I didn't create new stretch marks to get this thing back open. So another angle of that. And if you look towards the point of the brace, you can see the original stretch marks. Whenever you get a dent, it stretches the metal. So you have this extra layer of metal, or more surface area of the metal, because it got stretched in the dent. So, but there's ways to kind of feather that back in. I still never found out why the player never wanted me to unsolder the brace. Something very superstitious with taking the instrument apart. I don't know, maybe he thought there was something magical about it, but I got it done. So that's where I started. That's where I ended up. So these are just little things to address dents that just seem impossible. Here's one. This is a Shoki piccolo trumpet. There's the dent. This guy, same thing, was freaked out in the sense that he did not want anybody taking the instrument apart. It was a special gift from somebody, and why that made a difference, I don't know. But he had already asked about a half a dozen techs, can you get this dent out? That curved tube is actually tapered. So there's no way to get a dent rod. You can't reach at with a knuckle tool. So this is where the magnet comes into play again. Here's a little bit better picture of that. So same thing with the magnet. Get the largest dent ball you can, put it in there, and you just start tapping. And that's the finished product. I got the dent out without taking this apart. Again, painfully, I mean painfully slow in how it reacts. It takes a long time for that dent to come up, but it will come up.
Wayne, are we talking 20 minutes or 2 hours?
What's that?
Are we talking as far as painfully long time? I mean, are you talking about 20 minutes, or are you thinking like maybe 2 hours of just tapping?
20 minutes. Because, you know, if we had a dent rod that we could get to it, we'd have that out in less than 30 seconds. So for something to go longer than a couple minutes, it feels like forever. Okay. A little bit better view of that. So other places, trumpet bell crooks, euphonium knuckles, taper branches. There's tons of places to use this. I'm just wanted to kind of let you know, this just doesn't happen as quickly as our normal methods of taking dents out. So that's the only reason I say it's slow. So it takes a lot of patience. And a lot of times you're hitting the magnet so hard, you get the feel, I'm going to be flattening more stuff, but it doesn't really happen. I can't really explain it, but I've done this enough and always surprised at the results. Okay, now that pretty much ends this part. Do you guys, or ends the clinic, do you guys have any questions?
Kim, do you want to say your question out loud?
Sure. Yeah. So on that last example, as you're hitting it with a magnet and you've got the dent ball inside the tube, like that tube was kind of coming up at an angle from the joint. Are you having to support it somehow to keep it from bending?
I'm kind of, where's my branch? I mean, that particular thing, I'm holding it on both sides, trying to find my magnet here. There. See, there's a magnet. Okay. I'm almost kind of, sorry, holding it from the side like this. So I'm not trying to support it from underneath. I'm just holding it. It's strong enough. You're not going to bend that tube back down against itself. And with the ball being small enough that's inside, it's like I said, you tap this, that ball leaves the dent and then comes popping back up to the magnet. So it's that coming back to the magnet is what brings the dent up. But it feels kind of strange to be tapping on something you think, I'm going to make more damage. That's what it just feels like that. And then you take your magnet away. That's the other part. It's always hidden. It's always under the magnet what's happening. So you're removing going, something happening, and you get surprised. Little by little, that dent comes up. But it's really, I got to say, it's really slow compared to normal methods. Does that answer your question?
It does, thanks.
That pretty much is my presentation. A lot of unconventional ways to take dents out. And, you know, I have to think of creative things. I'm not the biggest, you know, I'm the strongest forearms. So me working on a tuba or sousaphone, I've always had to figure out creative ways to take dents out of really big instruments and things, but I've figured it out. You use your body weight, you use a lot of different ways to figure out how to make these things happen.
I have a question about what you do. So like whose instruments do you work on as in your job? Like Yamaha artists, professional musicians, anyone who comes into the shop?
Professional.
How does that work?
You know, to give you an example, my colleague Tomoji Hirokata, we see the who's who, the principal oboe, sax, but principal from every orchestra across the United States. I'll just say the big five, whoever you consider the top five orchestras. These are the players that we see. You know, somebody asked me, I was doing a clinic, and they know that Tomoji and I do repairs for professional players, and the comment was going, oh, you must hate that these guys think they're, you know, really important, they're divas, and I got to tell you, principal players or people that are really at the top of the field are probably some of the nicest people to do work with. I have had more problems with the guy who's the principal trumpet of the community band saying things to me like, do you know who I am? Yes, I do, but that doesn't fix our problem. Now, we work with everybody. So just about anybody you can think of. You know, as far as orchestras or even in the, you know, pop and jazz world, you know, everybody from Randy Brecker in my previous shop, Dizzy Gillespie, Clark Terry, Art Farmer. I've worked with a lot. I've been lucky where I've worked with a lot of great players, and it's just pure luck. Scared to death most of the time. Not that easy, because sometimes you're trying to stay as cool as you can be and not be nervous, and yet you got somebody's. Art Farmer brought this thing called Monette Flumpet. And I think that instrument at one time was valued at $35,000, but he dented the back of the bell. I have never hit a trumpet so hard to try to lift a dent up. And as I'm really hammering, I mean, as hard as I can hitting this thing, I realized on the receiver of his trumpet, there are these diamonds mounted, set in the receiver. And I'm looking at this going, how well are these diamonds set? They fall out. So every 2 minutes, I'd be counting 1, 2, 3, 4, 5. I'd be counting the diamonds to make sure something didn't fall out. So, there's weird, interesting stories like that, but I've been very lucky. I've gotten to work with a lot of great players. I don't want to really go into a list. So, hope that answers your question. Anything else you guys want to ask?
Gives me hope for dent work. It's not my forte. So
Just take time. One thing I will mention to you though, dent work. When I started doing dent work, I went to the Allied Repair School. Our dent ball set, we didn't have the benefits of having what nowadays you can buy dent ball sets where the dent balls, you can use a magnet to figure out where those are. When I started, our dent ball set was made of brass. So being a young student, we had to learn to listen. When are you on the dent ball? When are you on hollow tubing? You would listen for this high pitch. When you're on top of the dent ball, you get this additional higher pitch in the hit. So we had to learn to listen. And now I look back at that, that was my biggest benefit. That and being smart enough where the instructors, if you were really there for a couple months and doing dent work, somebody would look at you going, oh, you know what would make that easier? Just go ask this guy for the brass magnet. And so if you didn't think about it, you'd go and ask this guy, and then he would tell you he loaned it to this other guy who would tell you he loaned it to this guy. And if you didn't know, you'd be chasing around the shop trying to find the brass magnet until you caught on. Right. So we had the benefit of listening. So if there's one thing about dents is know where the dent ball is. The other thing is, I don't know where that's, oh, there it is. I don't know if you guys have these small magnets. There's a dent ball inside there. I know where that dent ball is. So sometimes having a small magnet is just knowing where that surface is. So if that helps you, get one of these small magnets. And, if you're working on the crook of the bell and you're wondering, until you learn to hear that sound of being right on top of the dent ball, because there's a definite clink with a little higher pitch ring to it. But use a magnet to kind of tell you where is that, or even the end of a dent rod. It's really helpful. That'll help you kind of clue in, this is where I'm supposed to tap, or this is the wrong dent ball. It's not going to get me where I need to be. So, but listening, I think, is probably one of the most valuable lessons, because you will hear a definite clink when you're on top of the dent ball, and listening for that. So nobody teaches you that. They just tell you, well, just put this underneath the dent and hit it. Well, there's a sound to that. There's a definite sound. And if you start to learn that, you gain this confidence for going, okay, I know where it is. I know I'm working exactly where I should be working. And that's the more important thing, because a lot of times you could be to one side of the dent ball or not on it, not at all. And then all of a sudden it's like, okay, now we're going to repair the repair. So if that's the only bit of advice. The other thing is, use some kind of lubricant on the dent ball if you have a deep dent. It'll help get it pushed underneath, because a lot of times if it's dirty or it's really dry, it's really hard to position the dent ball. Or using a dent rod, sometimes you will take a dent out and all of a sudden you see in the lacquer a big lacquer stretch or streak. Greasing it on the inside helps. It's not going to make it not happen, but it'd be a lot less. So, I always try to follow this thing where try to make it look like I was never there. Try to make it look like nobody ever fixed this. It was always like this, but it's not always possible. But that's what I try to shoot for. I hope that helps.
Thanks.
You're welcome.
Anybody else have any last minute quick questions?
Oh, we can go for another 3 hours. No. Well,
Thanks so much, Wayne, for joining us today and spending your time and your knowledge with students. It's really great. And everybody's going to say thank you on chat now. I will pass along your email to the rest of the students. That way, if they think of anything after the fact, they can reach out to you.
More than welcome to just ask me by email, or if they have questions, please just ask